Now, could we get any more evidence for something like this? And I'll just end with this. You might ask if something like this landscape is responsible for the smallness of the cosmological constant. What about the Higgs? And in fact, there's a similar issue, not quite as dramatic as the universe being empty. But remember, we just said if the vacuum energy was just a little bit bigger, the universe would be empty. What would happen if the Higgs particle was a little bit more massive? Then as it drags, remember I told you, as you drag up the mass of the Higgs, you drag up the masses of the rest of the elementary particles. And then if you just drag up the masses by a factor of 2, something, 2 or 3, something relatively dramatic does happen. You all know that the complicated nuclei are made out of neutrons and protons, but you also know the neutron is heavier than the proton, and in empty space, the neutron can decay to a proton. So why do we have a nuclei made out of neutrons and protons if the neutron can decay to a proton? It's because the binding energy of neutrons and protons inside a nucleus is actually is bigger than the mass difference between the neutrons and the protons. But that turns out to be a complete accident. And if you make the elementary particles heavier, then the quarks inside the neutron and the proton become heavier. And they make it so that the neutron-proton mass difference becomes larger than the binding energies already, just if you make all the particles heavier by a factor of 2 or 3. And so that means that if we just change the situation just a little bit, we would go from having all these complicated nuclei to just having hydrogen and nothing else. So there was another sort of big difference in the world if you just made the Higgs head in the direction that it wants to head by making it even more massive. So it's conceivable that there's a sort of a landscapey way of approaching the problem associated with the Higgs mass as well. But there are a lot of beautiful things about the old picture. There's a lot of beautiful things about the supersymmetric picture I didn't have time to explain, but it played very nicely with the notion of unification of forces at very high energies and made various quantitative predictions about that at the percent level that ended up being correct. There's a picture of dark matter associated with it. I haven't had time to talk about. But there is an interesting intermediate possibility that takes the landscape seriously, but says that the presence of the landscape could impact the sort of version of supersymmetry that we see, and that there could be a different version of supersymmetry that we called back in 2004 and 5 the minimal split supersymmetry, where half of the new particles associated with the superpartners are by this famous factor of Q squared, that number of around 100, 1 over 100 that I talked about, that parametric factor of 100, we make the so-called scalar superpartners 100 times heavier. The fermion superpartners would be left lying around and would be accessible at closer energies that would be associated with dark matter. This is a very unusual picture of supersymmetry. It would look fine-tuned from a conventional way of thinking about things, but is very reasonable with the landscape. And it made a correct prediction. This theory was proposed back in 2004 or 5. It correctly predicted that the Higgs particle should lie in this relatively narrow range between 120 and 135 GeV, which it did do. It was discovered at 125 GeV. So it's not a very impressive prediction, but it's at least not wrong. And anyway, that's my own best bet. If you're going to wake me up in the middle of the night and ask what I think is going on, I think some version of minimal split SUSY is probably right. But it could be that we would need to wait for the next generation of colliders to have high enough energies to make even these fermions of a SUSY. In this model, they can't be heavier than around sort of 5,000 GeV or 5 TeV. They could still be too heavy to be made at the Large Hadron Collider, but people both in Europe and in China are talking about a new set of colliders beyond the Large Hadron Collider. They'll be around 100 kilometers around and collide particles at around 100 TeV. The LHC is colliding particles at around 14 TeV. This is going to be a very big leap. You could use this big tunnel to collide electrons and positrons and produce millions of Higgs particles to put this unusual, bizarre new beast, the Higgs, to put it under a microscope and study the hell out of it. And later in the same 100-kilometer tunnel, you could collide protons up to around 100 TeV and probe what's going on with this deep question about the violent quantum mechanical fluctuations of the vacuum. The LHC is just in the neighborhood of sort of telling us there's something wrong with our old way of thinking, but not high enough energies to like tell us what's right in any very definitive way. So anyway, it's not guaranteed that these colliders will actually happen, but they're serious proposals of putting them forward. They have a chance of happening, and certainly I'm going to the gym and working out and hoping to someday see these 100 TeV collisions, because I'm pretty sure they'll discover these particles associated with split SUSY. So I want to be alive to see that. All right. Well, I think I'll probably end there. There's the last topic I wanted to talk about, but I've already gone so far over time, so I won't talk about this. If people are interested, we can talk about it in the question session. But what I hope to have done in this talk is shown you how these deep principles of space-time and quantum mechanics dictate the properties of the world around us. I think it's an incredible story. And B, how dramatic it is that those very principles are under great pressure. And we somehow have to find a new set of ideas that tells us where those principles come from, explaining why, on the one hand, they're so stunningly successful, and yet, on the other hand, how they could be superseded by things that are likely to be deeper and more abstract as we move forward in the 21st century. Thank you very much.
So there are no experiments, you think, which will suggest this, excepting whatever these large hadrons and so on that you want to construct. Nothing else, because for the between the multiverse and.
Well, I mean, you see, even even that, what if something like split SUSY was discovered, it would still not prove that there's a multiverse out there. In fact, that's our sort of big problem. We don't know how to build a telescope to see the other universes yet. Okay, but that might make you think, oh, it's all garbage. Probably, where it's like counting angels on the head of a pin. But it's a little bit similar to some very famous physics involving black holes. So living inside an accelerating universe is a little bit like being inside a black hole. So we have a horizon sort of outside. We can't see the things from the outside. Now, in the context of black hole physics, we've learned that classically you think you can throw something into a black hole and it's gone, but quantum mechanically it evaporates with Hawking radiation, and the information is supposed to come back out somehow. Okay, so now and exactly how it comes out and how to think about it is still under very active research by people who think about those things. But you can already draw kind of a parallel that in the same way you might think that things that are outside our cosmological horizon are sort of garbage, that we can't see them, we shouldn't talk about them, but maybe there's some quantum mechanical way that their presence can actually be seen inside our own universe. Okay, so now, but we don't know. We don't know either way. But the main problem is to build a telescope to see. Okay, and we don't know how to do that. So, but what we could do is get more examples of quantities that appear to be sort of crazily fine-tuned from one perspective, so that we can get more evidence of things that are that don't make sense from the standard perspective, but would make sense from this other perspective. It doesn't mean that it's right, but it'll give more of a psychological push in that direction. So the discovery of something like split SUSY would do that in a big way, because you would actually see, you would have evidence that the world is supersymmetric, but that supersymmetry did not bother to survive to low enough energies to solve all these problems, okay? Supersymmetry could have already solved the cosmological constant problem, and it didn't. It could have already solved this other problem with the Higgs, and it hasn't. So that might just lead you to think that it's just garbage. It's not, I mean, sorry, that it has nothing to do with these problems. But if you discover that it's actually sitting there, but refusing to solve these two problems, that's even more indication that there's something else going on. I mean, so now, these big colliders are the most direct way of looking for the new particles, but there's actually some beautiful tabletop experiments that can also look for them. There are many of them. There's now a thriving field of sort of tabletop experiments to look for very tiny effects that would still tell us that we're going beyond the standard model of particle physics. But my favorite one is to look for some substructure associated with the electron. So, the electron has charge, and you can think of it as a little spinning top because it has spin. But it could also have a non-uniform distribution of charge, and that would show up as an electric dipole moment. Okay, so to have some. Now, there's no evidence for an electric dipole moment of the electron. If you the kind of units of a dipole moment are length, right? Because it just says how much it's stretched out. The experimental limits on the electric dipole moment of the electron for many, many years were down to around 10 to the minus 27 centimeters. Okay, so that's that shows you how shockingly accurate these experiments are, because we are certainly not even seeing 10 to the minus 17 centimeters at the collider. Okay, so the limits are around 10 to the minus 27 centimeters. There was a real breakthrough around 7 years ago by a group at Harvard and Yale, the Acme collaboration, Jerry Gabriels, John Doyle, and Dave DeMille, and they improved things by a factor of 100 over the past 7 years or so. Factors of 10 an experiment, make a career. Factors of 100 are a real breakthrough. And they're going to go another factor of 100 in the next 10 years. Okay, so they're going to get down to around 10 to the minus 31 centimeters. The reason I bring this up is that in split SUSY, it's not a sharp prediction, but you expect that the dipole moment should be between 10 to the minus 28 and 10 to the minus 31 centimeters. From the effect of these very heavy particles, they should give a little dipole moment at that size. So you see they're down to 10 to the minus 29. So they've already cut into the parameter space a little bit, but we have sort of 2 orders of magnitude to go. And so I'm very excited about these experiments. If they see something, again, it would be sort of consistent with what we'd have expected from split SUSY. And there's some other experiments like that. But so it's not just giant colliders. Giant colliders are necessary for our business. They're really necessary. Because we go to the high energy frontier to see what's there. But B, even without just this fishing expedition, it's really necessary to put the Higgs under a microscope and study it to death. It's a very weird particle. For the reasons I was trying to explain, we've never seen anything like it before. For very good reason, we've never seen anything like it before. And yet we've seen it. It hasn't been, its origin has not been explained in the way people expected it to be explained for 40 years. So so it makes sense to put it under a microscope. So that's the main thing that these new accelerators would do. But then beyond that, we'd also go to the higher energies just to see what is around. The time scale for those things is 20, 30, 40 years if they happen at all. So in this business, you have to get used to very, very long time scales for progress. Of course, it's something that mathematicians are very used to. One of the things I love about interacting with mathematicians is that worrying about things that might take 100 years is not a problem for mathematicians. And I think we have to get used to similar timescales in the fundamental physics. We are spoiled in the middle of the 20th century by a period of sort of very rapid progress. But it's a period of very rapid progress because it was not quite as revolutionary as the things that came before, and I suspect as the things that will come now. That progress is very rapid because the intellectual framework in which to understand things was set, and it just had to be filled in. Now we're at a moment where we have to really take another step, and so it's I think it's going to be similarly challenging.
Okay.